When we look at amides, we know that amides are the least reactive of our carboxylic acid derivatives. So we should expect that if we need to reduce an amide, we're going to need to use our strongest reducing agent, which is lithium aluminum hydride. So if I have a primary amide, like the one that you see here, and I treat it with lithium aluminum hydride followed by a water workup, I'm going to make a primary amine. Notice that my water workup conditions are different than the acid workup conditions that I saw before. That is because if I have an amine under acidic conditions, that amine will be protonated. And so I want to be able to stop this reaction at the neutral amine. So by using just a water workup, I can quench my reaction, stop the lithium aluminum hydride from further reacting, and I can make the amine out of this reaction. If I have a secondary amide like this one here, notice that here I have the carbonyl and I have a second alkyl group on my nitrogen. If I treat this secondary amide with lithium aluminum hydride followed by my water workup, I get that secondary amine. So I'm not changing any of my carbon-nitrogen bonds that I have. I'm simply introducing hydrogens in order to replace that carbonyl. So where my carbonyl was here, I now have 2 hydrogens for that secondary amine. I did the same thing up above for the reaction of the primary amide. If I have a tertiary amide like this one here, and I treat it with lithium aluminum hydride followed by a water workup, I make a tertiary amine. Again, the carbons that were bonded directly to the nitrogen here as the alkyl groups remained the same. My 2 hydrogens that were added replaced this carbon-oxygen double bond at this position here. Now, keep in mind that you know further reactions of primary and secondary amines. You could use them in a reaction with an acid chloride or an anhydride or an ester in order to make amide compounds. We'll look at an example of that later on. The next functional group to talk about is acid chlorides. And what we know about acid chlorides is that these are our most reactive functional group. So that these compounds sat at the top of our reactivity trend that we had for our carboxylic acid derivatives. That means that our most reactive reducing agent of lithium aluminum hydride will certainly react with my acid chloride, but this is going to also be where I see the introduction of my weaker reducing agent for sodium borohydride. So let's start first with the lithium aluminum hydride. Remember, this is a strong reducing agent that reduces absolutely everybody. So if we treat my acid chloride with lithium aluminum hydride followed by an acid workup, I will make a primary alcohol. This is accomplished through the addition of 2 hydrides at that carbon of the carbonyl. Sodium borohydride, as my weaker reducing agent, behaves very similarly in its mechanism. So here I have a boron with 4 hydrogens bonded to it. That boron carries a formal charge of -1, and so this boron can send one of the hydrogens with its electrons towards the carbon of the carbonyl and give me a tetrahedral intermediate. We know that this tetrahedral intermediate can collapse and kick out the best leaving group. In this case, my leaving group choices are the chloride, the hydrogen, or the phenyl ring. And remember that the phenyl ring and the hydrogen are never leaving group choices. So my only choice is to lose that chloride ion. When that happens, I get an aldehyde. And just like we saw before, that aldehyde can further react. A second equivalent of my borohydride ion can send the hydrogen with its electrons to the carbon of that carbonyl, push the electrons up to the oxygen, and that's going to give me a tetrahedral intermediate that looks like this. This tetrahedral intermediate has no groups that it can lose, so this tetrahedral intermediate is stuck. This is what I have at the end of step 1. Upon protonation, when I introduce my acid at the end of step 2, I can now protonate and form my final alcohol product out of this reaction. So because my acid chlorides are so reactive, they will be reduced to primary alcohols using both of my reducing agents, my strong reducing agent of lithium aluminum hydride and my weak reducing agent of sodium borohydride. The next reduction of an acid chloride is a unique reduction. This is one that takes place in the presence of hydrogen gas and palladium on barium sulfate. And under the conditions of this reaction, the chloride of your acid chloride gets converted to a hydrogen. So we transform our acid chloride to an aldehyde. Finally, the last reduction is nitriles. And remember that nitriles are like amides, so they're not a very reactive functional group. And so our nitriles are going to require lithium aluminum hydride as their reducing agent. Now, with this reduction, our nitriles are going to be converted to the amine, just like our amides were converted to amines as well. And because our products are amines, we need to be careful with our workup conditions, and we need to make sure that our workup conditions are under water conditions or aqueous conditions rather than acidic conditions. Remember that anytime you have an amine, whether it's from the reduction of a nitrile or the reduction of an amide or just an amine, and you have it under acidic conditions, it's going to be protonated. So anytime you have acid around and an amine, there's always going to be an acid-base reaction that occurs between these two components, and we're going to end up with that protonated ammonium. So in this case, it would look like that. Okay, so in this case, our nitrile gets reduced with lithium aluminum hydride to the primary amine. Notice that nitriles, because we start out with that carbon-nitrogen triple bond, the only amine product we make is that primary amine. So we're going to replace both of these carbon-nitrogen pi bonds with 2 hydrogens being added to the carbon and 2 hydrogens being added to the nitrogen. The last reaction is the hydrogenation of the nitrile, and this is a reaction that we already talked about. We talked about this reaction in our discussion of electrophilic aromatic substitution for exam 2. And so if we treat a nitrile with hydrogen gas and platinum as our catalyst, we also make the primary amine. So nitriles reduce to amines, amides reduce to amines. And also keep in mind that for nitriles, like this one, when you have a nitrile that undergoes your hydrolysis conditions, so HCl, water, and heat, remember that your nitrile hydrolyzes to a carboxylic acid. So nitriles reduce to amines and hydrolyze to carboxylic acids. Make sure you pay very careful attention to that and make sure you know how to answer questions on both of those reactions.